Well, hello, everybody, and welcome to our tour of the universe. Now, this is going to be a little bit different than maybe some of the other shows you've seen at the California Academy of Sciences. This is a program that is going to be completely live, and I am using a planetarium software called OpenSpace. It's open source planetarium software that actually can be downloaded onto laptops as well as computers. And we are going to travel to the edge of the visible universe and all the way back home. We're going to start our tour of the universe today, relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And the ISS is as far as humans do travel nowadays. You can fit about 6 astronauts on it at any one time, and it is the largest thing that has been built in space so far. It's about the size of an American football field, or I like to say the Academy of Sciences. So if you have actually walked from one side of our building to the other, you have actually walked the length of the International Space Station. Now, it looked as if the International Space Station, or ISS for short, kind of dove right back into Earth. That's because we are actually falling very far away. And to help us keep track, I'm actually going to go ahead and bring up the path of the ISS around our planet Earth in kind of this orangish color. Now, as we pull away, you might see that part of our planet doesn't seem to have any actual clouds, and that's because we are actually using real data to show you what it's like. This is clouds as of yesterday, and the clouds on the other side just haven't downloaded yet. But we can actually see the ISS is traveling around our planet pretty fast. It's actually as fast as humans do travel nowadays. But we're actually going to go much, much further away from our planet. We are going to travel and see how far our human influence has gone. We'll see how far humans have physically traveled, how far our spacecrafts have gone, and how far human communications have gone as well. But for now, the ISS is as far as humans do travel, although there are some plans to go back to the moon relatively soon, and hopefully one day go to Mars. In the meantime, as I mentioned, they are traveling pretty quickly. In fact, it takes them about 90 minutes to orbit us just once. So I'd like somebody to try to do that math and figure out how many New Year's days does the ISS astronauts have this evening or tomorrow morning, wherever you are, when it takes everybody else to have a New Year's. That'd be a very interesting mathematical question. I'm sure it can be done. I just haven't done it off the top of my head. But let's go ahead and continue our journey. And as we zoom on out, I'm going to go ahead and bring the paths of some of the other objects in our solar system, like our planets and even the moon. We can see that ring around the moon, or around Earth, or what looks like a ring. It's just showing the path of the moon. Let's actually go ahead and just look at the moon's path. Now, the moon is our closest natural neighbor, and it is as far as humans have traveled into space. The Apollo astronauts came out here in the 1960s, and it took them 4 days to get to the moon. Now, even though the moon is relatively close, it doesn't mean it's close in human terms. The moon is about 250,000 miles away from our planet. And as we get further and further out, we're actually going to go to distances of billions, trillions, and even sometimes quadrillion miles. And when we get to these large distances, it actually doesn't make sense for us to use measurement of distance like miles and kilometers anymore. So we're actually going to use a different yardstick, so to speak, the speed of light, the fastest thing that we know of. Now, if you could actually travel the speed of light, which is 200,000 miles per second, it would take you 1.5 seconds to get to the moon. So we say that the moon is 1.5 light seconds away. But now that we've zoomed in into the moon's surface, the moon gives an illusion that it's actually been hit by maybe asteroids or comets or meteors more often than us. We actually get our fair share of impacts here on Earth. And remember, Earth is actually a bigger target. The thing about the moon is that it has no atmosphere. So there's no weathering and there's no erosion. Also, there's no plate tectonics moving around and erasing things. So once something hits on the moon, it actually never disappears, unlike Earth. But we can go ahead and look a little bit closer and see the path of the moon around our planet. And let's go ahead and zoom on it just a little bit. Now, the moon's orbit around Earth is about a month, or I like to call it a month because it's not a full month, it's actually 29.5 days. But let's go ahead and bring up the paths of those other objects in our solar system, or the larger ones at least. We can see the path of Earth as we zoom away, and we can start seeing the paths of those planets. If we start close to the sun, the closest one to it is some rocky planet called Mercury. Then further out would be Venus, then Earth, that third rock from the sun, and then Mars. Now, if we could travel from Earth to the sun, and we were traveling the speed of light, it would take us 8.5 minutes to get to the sun. So we say that the sun is 8.5 light minutes away from us. We can also start to look at the paths of some of the other planets in our solar system. We have the gas giants, Jupiter and Saturn. And even further out, we can start to see the paths of the icy giants, Uranus and Neptune. Now, when we look at the solar system kind of from this top view, we can see there's actually a sizable gap between Mars and Jupiter. But it's not empty space. There's actually quite a lot of things in this area. This is actually our asteroid belt. I can also bring the paths of some of the asteroids up. Now, these aren't all the asteroids that we know of. I'm actually showing you probably about 70% of them, because if I showed every single one in its path, my computer would actually crash. It's just too much data. But while we're looking at this view, I like to pause here for a moment and take a look at a little less known object. It's an interesting object. I'm going to go ahead and bring up its path as well. Might be a little hard to see, but if we zoom on in just a little bit, you can see it kind of in this light blue color. Going straight through our main asteroid belt. Any ideas of what this might be? Well, if you all said Ceres, you're absolutely correct. So Ceres is a little less known object, and it's okay if you have never heard of it before. Ceres is what we call a dwarf planet. And I bet you might know of another dwarf planet in our solar system. That is Pluto. And we can bring up its path as well in the outer parts of our solar system. Now, the reason why I like to point out Ceres is because Ceres and Pluto actually have pretty similar stories about how they're categorized or how we name them. So we found Ceres about 300 years ago using our eyes. And we thought it was actually the only thing orbiting in between Mars and Jupiter. So they named it a planet. And around that same time, we started using telescopes, and we started finding smaller rocky objects that were in this area as well. And they called these small rocky objects asteroids. So since it was in the same area, they decided, okay, we're going to rename Ceres from a planet to an asteroid. And similarly, this is what happened with Pluto. When we first found Pluto, we thought it was the only thing orbiting out here. But in the late 1990s and early 2000s, as astronomers' telescopes got better and better, we started finding even more objects in our solar system. Now, most of these are small icy objects, but some of them are actually quite big. I'm going to go ahead and bring up the paths of those objects as well. So these objects are what we call trans-Neptunian objects. And this is, we can see, kind of similar paths as Pluto. So we realized we needed a new category for Pluto. So they figured out that Pluto and Ceres are kind of similar. They go through these kind of really crowded areas. So they decided, okay, let's come up with a new term. It's not quite a planet. It's not an asteroid. Let's call it a dwarf planet. So I know some people were kind of disappointed that Pluto got demoted, but I like to think of it this way. Yes, Pluto got a demotion, but Ceres got a promotion. So we've traveled kind of towards what we might consider the outer parts of our solar system. I'm going to go ahead and turn off some of these objects because they tend to slow down my computer. We have much further to go. But let's recap as how far we have actually gone out into space. So a reminder, it takes us 1.5 seconds to get to the moon at the speed of light. So we say that it's 1.5 light seconds away. The sun is 8.5 light minutes away from planet Earth. Now, if we could go from one side of Pluto's orbit to the other, it would take us 10 hours traveling the speed of light. So we say that is 10 light hours across. But even out here, we can actually check in on our human influence. We can see how far our spacecrafts have gone. So we can go ahead and bring up the paths of some of the fastest and farthest spacecrafts. We have Voyager 1 and Voyager 2, and Pioneer 10 and Pioneer 11 that were sent out in the 1970s. And more recently, we have New Horizons that went by Pluto back in 2015. Now, these are the fastest and farthest spacecrafts have gone, but none of them have traveled the length of distance as far as light can travel in one day. We're getting close, but still under one light day. Okay, let's continue our journey. We still have quite a bit to go. And we'll start to fly past some of the other stars in our galaxy. Now, the closest star to us, beyond the sun, of course, is about 4 light years away from us. So it would take us 4 years to get there. We were traveling the speed of light. But even way out here, we can actually check in on our human influence one last time. This is what we call the radiosphere. It's an imaginary sphere of how far our radio signature has gone out to space, or radio and television signals. Now, the earliest radio signals that were strong enough to escape our planet was sent out in about the 1930s. So this is about 90 light years away from us, or 95 light years away from us in all directions, since all radio signals are traveling the speed of light. And we can actually even see how many planets we have found outside of our solar system, what we call exoplanets. So every ring is around a star that has at least one confirmed exoplanets, and many of them actually have multiple planets we have found. And if you actually look inside that radiosphere, we can actually see there's quite a few exoplanets that we have discovered. So who knows? Maybe there's actually somebody listening to Nat King Cole right now. That'd be pretty neat. All right, let's keep going. We still have to get outside of our own galaxy. Everything we've seen so far is still within our own Milky Way. Now, as we zoom on out, I want you to keep an eye on that radiosphere. See how long it takes for you to lose it or be able to still see it. But now we are actually starting to see the large scale structure of our own galaxy, the Milky Way. We live in what we call a barred spiral galaxy. It's shaped with these kind of flat discs and with these beautiful spiral arms that are made of gas, dust, and stars. And right at the center is a bright group of stars really close together in our galaxy. Now, if we could actually see past all of that, right at the very center, you'll see, well, basically nothing, because there's a supermassive black hole at the center of our galaxy that is about 4 million times the mass of our sun. Okay, do you still see that radiosphere? All right, I'm going to use my cursor. It's right here. That's our radiosphere. That's our little part of the galaxy. And that's how far humans' communication has gone out into space. So we are now at distances of light years. If we could go from one side of our galaxy disk to the other, it would take about 100,000 light years. So we say it's about 100,000 light years across. Now, our galaxy has roughly about 400 billion stars in it, but it's just one galaxy out here. As we continue out, we'll start to see where other galaxies are. Every dot we see now is not a star, but its own galaxy, with its own billions and sometimes even trillions of stars. And these colors may seem like, somebody accidentally spilled some Skittles into the universe. These aren't the actual colors of the galaxy. It shows us the different surveys that are mapped these galaxies. So as we zoom on out, we can start to see kind of what we call the large scale structure of our universe. And you may notice some things that look a little funny. One is, they look like our universe is shaped like a bow tie or a butterfly. This is not the case. It's because of our own perspective. We are the ones making the map. As we look out, we are seeing everything around us, which actually makes us seem like we're the center of the universe. That's the other kind of funny thing. But because we are looking out, sometimes things block our view. Remember I told you that our galaxy is made of gas and dust and stars? Well, the gas and dust actually blocks our view, so we can't see beyond our own galaxy. So where we see these kind of empty regions, these really giant black areas, it's not that there's no galaxies there, it's just we haven't been able to map them. We're pretty sure there are galaxies there. We just haven't seen them. And hopefully soon we'll be able to start mapping them a little bit better and better. As our technology gets better and better, we can start seeing through some of the gas and dust of our own galaxy. Okay, we got to continue our journey because we still haven't gone all the way out to the edge of our universe yet. And as we zoom on out, we'll start to see some of the earliest objects in our galaxy, or our universe, what we call quasars. Now, I do mean earliest because anytime we are looking out into space, we're kind of time traveling in a way, because the light of those objects has to travel so far, travel all that distance, and gets into our telescopes. We are seeing the light of those objects as they were in the past, not how they look today. So, for example, remember we were looking at those stars close to us, about 4 light years away from us? Well, that's how they looked 4 years ago, not how they look today. And now we're seeing the universe as it was billions of years ago. And because of that, there's only so far that we can go. There's an edge to everything that we see in the universe. And that edge we can now see all around us. This kind of orange blotchy thing is what we call the cosmic microwave background, or CMB. And what we're seeing is different fluctuations in temperature in the early universe. Now, if you had a radio telescope and can actually see in the microwave range of light spectrum, you would actually see this everywhere you looked in the sky. In fact, the first radio astronomers were really confused when they were looking up in the sky with their telescopes, and they're like, what is going on? Why are we seeing so much interference everywhere we looked? But soon they realized that it was actually something they were seeing out in space. This is a few 100,000 years after the Big Bang would have happened. So you can kind of think of this as the baby picture of our universe, the first light that we can see. But since this is the edge of everything that we can see, that means we can't go any further. So this is the end of our journey. We're going to go ahead and start heading back home. Promised you I wouldn't leave you out in space. But as we're traveling, if we were that far out in space and we're actually flying the speed of light, it would take us 13.7 billion years. But thankfully, we have our planetarium software, so it's only going to take about a minute. And one more thing I want to point out as we're zooming back home. Everything that we've seen so far, all the stars and galaxies and the cosmic microwave background, that's not everything in our universe. There's dark energy, this mysterious force that's causing space itself to accelerate as it expands. And there's dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and at the edge of galaxies especially. And we call all these things dark energy and dark matter because, well, we're not quite sure what they are yet. But we do know that they make up 96% of our universe. So everything that we have seen so far is only 4% of everything that is out there. And that may make us feel a little small, like we're one tiny dot in this homogeneous universe. But I like to think of it this way. Yes, we're one tiny dot, but look at all that we have found so far, almost entirely by looking through telescopes. And there's so much more for us to discover and so much more for us to learn about. And that's what makes it a wonderful time in human history. We're not just able to learn about all these things, but we're also able to show them like this, a map of the cosmos in 3 dimensions. And we're just starting to unravel the true nature of our universe. But we're only just starting. The rest, well, that's out to the next generation of scientists back here on planet Earth. So as we approach and see the sun light fly past the fastest and farthest spacecrafts that we've sent out, we're heading back home to that third rock from the sun, the only place in all of this that we have found life. And that's pretty incredible to think about. So welcome home, everybody. And thank you for joining us for our tour of the universe. If you want to learn more about OpenSpace, the software that I've been using, you can go ahead and click the link that's going to be in our comments, as well as we'd love to hear how you like this program. It is helped and funded by NASA. But I want to say thank you, everybody, for joining us. I want to say a warm thank you, everybody, for listening in from the Morrison Planetarium and the California Academy of Sciences. And I hope you have a great rest of your evening and Happy New Year.